Now we are going to discuss randomized complete block design with sampling. This is a traditional RCBD model, so no any sampling effect there in the model. But after having samples, we need to include the sampling effect or otherwise sampling error into our model. As we had with CRD with sampling, we will have a source of variance for error in sampling error. Calculation of experimental error degrees of freedom is done the same way as if there was no sampling. Calculation of the sampling error degrees of freedom is done the same way as was done for the CRD with sampling. So we can use the same way as we use sampling in CRD. Now, under the each replication, we are having two samples. So we have three treatments. We have three replications. Under each replication, we are having two samples. So this is the case. Then this is the way of doing calculations. These are the steps. This is the first step. We can calculate the correction factor. So we can take the brand total and the square value of brand total, and we can use the amount of replications, amount of treatments, and amount of samples to capture this one. So this is the estimated value for the given data set. And the total sum of the square, we need to take the squared value of each observations, or each observation we need to take the square value, and finally we can take the summation of those all, and we can reduce the correction factor. Then you will have this answer. You can check. Please follow these steps and write down the equations and do the calculation in your way, and again compare your answers with the given answers in the video. So that's the way you should learn. Then calculating the replication sum of the square, you can take the summation along with each samples and along with each ith values. Ith values are representing here the treatment. So we have to take the replication sum of square. So there are three replications. So we have collected all things along with three replications. So finally we will have three values. Along with each replication, we have only three replications. Then we can take the square value of that one. Then for the denominator part, we are having some adjustment here with the effect of sampling. We can reduce the denominator under the each treatment. There were three treatments. Under each replication, there were three treatments. The three T is representing the amount of treatments, and S is representing here the amount of samples. So 3 by 2 is using here. And to calculate the treatment sum of the squares, you can take the summation of all treatments individually. So you will have only three answers finally. Then we can take the square value of those things, and as we discussed earlier, we can divide it by the amount of replication times the sample. So 3 times 3 times 2 is coming in this way, and finally we can reduce the correction factor. Then you will have this answer. And the adjustments for this sampling effect, then calculate SS among experimental unit totals, sum of this gamma experimental unit totals. So this is the calculation stage. So we are having the summation along with each sample, because the dot notation is for the S. So we are taking the summation along the sample. So in the first case, the summation of these first sample is, second sample, 160. Likewise, we can take all values. Then S is representing the number of samples. So we can, there were two samples in our case. So we can divide it by the 2. And finally, we can take all summation of these all and reduce the correction factor. Then we will have this answer. So experimental error, sum of the square is coming with these adjustments. SA EUT minus SST adment and replication. So following this one, we can take that one. Then we can create our ANOVA table in this way. Then sampling error you can take by reducing the SSAU AEUT by the sum square total. So the sampling error is in this way. So finally, you will have this answer. So unity state hypothesis separated by the replication and treatment. Still, we are testing the effect of treatments and replications on our response variable, but we have gathered unexplainable variation via more information. So we have gathered anyhow. We have reduced the fraction of explainable variation in this case using the sample error either. So as we discussed earlier, here also we can conduct comparison estimations. We will discuss about that later along with that mean separation procedure. Okay, thank you so much for hearing to this lecture.